Alright, let's tackle a question so big, it makes black holes look like tiny pinpricks. Where did everything come from? Seriously, take a moment to just think about that for a second. We're talking about absolutely everything. You, me, your cat, who is probably judging us right now. This video, the stars twinkling in the night sky. It all had to come from somewhere, didn't it? To really appreciate how mind-boggling this question is, let's consider just how much everywhere we're talking about. The observable universe stretches a staggering 93 billion light-years across. That's so far, it would take light itself almost 93 billion years to travel from one end to the other. And that's only what we can see. Who knows how much more lies beyond our current view, shrouded in mystery and potentially governed by laws we haven't even begun to understand. Now, most folks probably associate the origin of the universe with the Big Bang, that iconic moment of explosive creation. And yeah, it's a pretty good story. Everything squished into an infinitesimally small point, then poof, boom, expansion. But what if I told you that the Big Bang itself might need explaining? It's like saying everything came from this tiny explosion, and then asking, okay, but where did that tiny explosion come from? We're just pushing the question further back, aren't we? Look, let's be upfront. Nobody has all the answers. Cosmology is a frontier science. It's constantly evolving as we gather more data and develop new theoretical models. And sometimes those models get delightfully weird. What we do have are some pretty fascinating ideas, ranging from the plausible to the utterly bonkers, that attempt to address this fundamental mystery of existence. And honestly, just exploring them is a journey worth taking. It's not surprising that humans throughout history have grappled with this question. It's woven into our very fabric. We are inherently curious creatures. We want to understand our place in the cosmos, to make sense of why we're here and what purpose, if any, we serve in this vast, swirling expanse of time and space. Perhaps finding an answer or even getting a little bit closer is part of that inherent drive. Okay, let's talk about the Big Bang, which is currently our most accepted explanation for how the universe began. And before you picture a gigantic explosion throwing galaxies everywhere, let me gently correct that mental image. It wasn't an explosion in space, but rather an expansion of space itself, kind of like baking raisin bread where the dough represents the cosmos, and the raisins are galaxies slowly moving further apart as the dough rises. Imagine everything, all the matter and energy we know about, packed into a ridiculously tiny volume, hotter than anything you can possibly imagine. Then suddenly, it begins to expand. This wasn't some event that happened somewhere, it was everywhere simultaneously. Now, how do we actually know this is what happened? Well, there's a bunch of really cool evidence supporting the Big Bang Theory, and it all points towards this incredible expansion. The first piece of compelling evidence comes from something called redshift. Just like when a train whistle sounds higher as it approaches you, shorter wavelengths, and lower as it moves away, longer wavelengths, light from distant galaxies is stretched out, shifted toward the red end of the spectrum, suggesting they're moving away from us, and the further away they are, the faster they're receding, which perfectly aligns with an expanding universe. Next up, the cosmic microwave background radiation, or CMB. Imagine that tiny hot volume we mentioned earlier. As it expanded, it cooled down. This leftover heat is still detectable today as a faint glow across the entire sky, and it's remarkably uniform, but with tiny temperature fluctuations that actually seeded the formation of galaxies later on. Think of it like the universe's baby pictures. They're blurry but full of vital information about its earliest days, and scientists have painstakingly mapped this radiation to incredible detail. Finally, there's the abundance of light elements in the universe, specifically hydrogen and helium. During those incredibly early moments after the Big Bang, conditions were just right for nuclear fusion to create these elements, and the observed ratio of hydrogen to helium matches almost exactly what scientists predict based on the Big Bang model. It's like finding a perfectly matched recipe from billions of years ago, confirming that the ingredients and cooking process unfolded as we believe they did. It's frankly astonishing how well this all fits together. But here's where things get interesting. While the Big Bang Theory is incredibly successful at explaining how the universe evolved after its initial moments, it doesn't really address what kicked everything off or what, if anything, existed before. That tiny, hot volume, where did it come from? That's a question that pushes us right to the edge of our current understanding and beyond, hinting at even more profound mysteries lurking just out of reach. So while we can describe the dance, we haven't quite figured out who set the music playing yet. Okay, let's talk about the Big Bang. but not in a celebratory way, more of a we have a problem kind of way. The Standard Model paints this incredible picture of everything expanding from an incredibly tiny point, a cosmic egg if you will, and that moment is what we call t=0 or time equals 0. Now, mathematically, things get really weird when you try to describe what was happening at that moment because it implies the density and temperature of the universe were infinite, yes, truly infinite. Imagine trying to cram an entire library into a space smaller than your pinky nail and then squeezing even more in. It's not just uncomfortable. It's physically impossible, at least according to our current understanding of physics. Think about it this way. You know those times when you're driving along, everything's smooth sailing, and suddenly, bam, your GPS glitches out? It spins wildly, gives you a completely nonsensical route, and you realize the system just broke down. That's kind of what happens to our equations at the singularity. They start spitting out infinity as an answer, which is basically math's way of saying, I don't know. Because infinity isn't really a number, it's more like a flashing red warning sign that something fundamental isn't quite right. Now, you might be thinking, well, maybe infinity is the answer. Maybe the universe really was infinitely dense and hot. And that's a valid thought, but here's the rub. Our laws of physics, gravity, quantum mechanics, all those amazing things we use to understand the cosmos, simply can't handle infinity. They break down. They cease to be useful tools. It's like trying to build a house with Lego bricks that suddenly turn into pudding. The whole project collapses under its own weight. This breakdown isn't necessarily proof of anything, but it does suggest something significant occurred, something we don't fully understand. The singularity represents a boundary in our knowledge, a point where our current theories simply can't penetrate. It's the cosmic equivalent of hitting an invisible wall while trying to explore a new continent. We know there's something beyond that wall, but we lack the map and compass to navigate it. And this leads us to the big question, what came before t=0? Now, before you start picturing primordial soup or cosmic kittens playing with black holes, let's be clear, we honestly don't know. The concept of before might even be meaningless in this context. Time itself might have emerged with the universe, so asking what happened prior to its existence could be like asking what color is beyond blue. It's a question based on an assumption that doesn't hold up. It's mind-bendingly weird, I know, but that's precisely why it's so fascinating. Okay, let's dive into something truly mind-bending, a concept so strange it makes black holes look like fluffy kittens. We're talking about quantum fluctuations and their potential role in the universe's origin story. Now, you probably think of empty space as, well, empty, like absolutely nothing there. But trust me, that's a seriously misleading picture painted by our everyday experiences. Imagine trying to describe the internet to someone who has never seen electricity. It's simply not possible. Quantum mechanics, which governs the tiny world of atoms and particles, tells us something wildly different. That empty space, or what physicists call the vacuum, isn't truly empty at all. It's more like a bustling metropolis of temporary existence. A constant bubbling and popping of virtual particles appearing and disappearing faster than you can say, Schrödinger's cat. Think about it, if you could slow down time to an unimaginable degree, you'd see these ephemeral particles wink in and out of existence all around you. They're fleeting visitors to our reality. These temporary particles aren't just theoretical curiosities either, they have measurable effects. They appear as virtual particles because they violate energy conservation for a tiny fraction of time, borrowing energy from the universe itself before quickly annihilating each other and returning it. It's like a cosmic loan with an incredibly short repayment schedule. This phenomenon is actually crucial to understanding how electrons behave around atoms. Without these virtual particles mediating interactions, matter as we know it simply wouldn't exist, so next time you thank gravity for keeping your feet on the ground, give virtual particles a nod of gratitude too. Now, here's where things get really interesting and delightfully speculative. What if one of these quantum fluctuations, instead of just popping into existence and then vanishing, somehow amplified? What if this tiny blip in the vacuum, this momentary violation of the rules, became incredibly large, so large that it triggered the expansion we observe today as the Big Bang? It's a bold idea, I'll admit, but let's explore it after all. Even the wildest theories start with a what if. The beauty and challenge of quantum fluctuations is their probabilistic nature. They are fundamentally unpredictable. We can calculate the likelihood of them happening, and we can describe their properties, but pinpointing when or where one might occur is impossible. It's like trying to predict which grain of sand will be next to get blown away by a breeze. This inherent randomness opens up the possibility that the universe itself could have arisen from such a random event. It's a cosmic roll of the dice, and we just happen to win, or at least exist in the resulting outcome. Okay, so we've talked about the Big Bang. A pretty spectacular explosion, right? But as scientists dug deeper, they realized something wasn't quite adding up. It was like trying to build a house with mismatched bricks, and those mismatches created some seriously puzzling questions that the original Big Bang theory just couldn't answer. So enter cosmic inflation, which is basically the universe hitting fast forward on steroids. Imagine taking a tiny speck smaller than an atom, we're talking mind-bogglingly small here, and in less than a fraction of a second, expanding it to roughly the size of a grapefruit. That's kind of what happened, but with everything. One of those issues was the horizon problem, which is as intimidating as it sounds, but really just means that different parts of the universe appear remarkably uniform in temperature, even though they shouldn't have had time to interact with each other given how quickly everything expanded after the Big Bang. Picture two friends who live on opposite sides of Earth and haven't spoken for billions of years. How could their pizza preferences be so similar? Inflation solves this by suggesting these regions were in contact very early on before being rapidly stretched apart, allowing them to reach a thermal equilibrium. Then there's the flatness problem, which is about the universe's geometry. Think of it like a balloon. If you pinch and release it once, it's curved. However, observations show our universe appears incredibly flat, almost suspiciously so, and according to Big Bang models without inflation, it would have needed to be perfectly flat initially, which is about as likely as finding a perfectly round square. But again, inflation comes to the rescue by stretching any initial curvature out to such an enormous scale that it appears flat today. It's like smoothing out wrinkles on a gigantic tablecloth. The driving force behind this rapid expansion is something called the inflaton field, which, let's be honest, sounds like a superhero from a very obscure comic book, and we don't really know what it is. But imagine it as a temporary, super powerful energy density permeating all of space, kind of like an invisible elastic band pulling everything outwards with incredible force. The exact nature of this inflaton field remains one of cosmology's biggest mysteries, which is a fancy way of saying we have no idea, but physicists are working hard to figure it out. Now, here's where things get really interesting. If inflation actually happened, and all signs strongly suggest that it did, then the tiny region that underwent this rapid expansion could have been just a bubble within a much larger, possibly eternal, pre-inflationary universe. This means our observable universe, everything we can see, might be just one small island in an infinite cosmic ocean, which is both humbling and slightly terrifying to contemplate. It's like realizing your favorite beach is actually part of a much larger coastline that stretches beyond the horizon, suggesting there's more out there than meets the eye, or telescope, for that matter. Okay, so we've spent some time poking holes in the Big Bang theory. Not because it's a bad theory, mind you, but because things get a little sticky when you really start digging. What if I told you that what we consider the universe is actually just one tiny bubble floating in an infinite ocean of other universes? Sounds like science fiction, right? Well, buckle up, because the concept of the multiverse, the idea that our observable cosmos isn't everything there is, has some surprisingly solid theoretical foundations, and it offers a fascinating alternative explanation for how things got started. Let's start with eternal inflation, which is essentially an extension of the inflationary period right after the Big Bang. You remember inflation, right? The moment when our universe expanded faster than the speed of light. Yeah, that was weird. Eternal inflation suggests this rapid expansion didn't just stop. It keeps happening in some regions while others cool down and form universes like ours. Think of it like boiling water. Bubbles constantly pop up, each a separate universe with its own set of physical laws and constants, all spawned from the same underlying mother space, which itself might be part of an even larger multiverse. Then there's brain cosmology, and this one gets delightfully weird. Imagine our universe isn't a three-dimensional space but rather a giant sheet, or brain, floating in a higher dimensional space called the bulk. Now, picture other brains, also universes, existing alongside ours, perhaps vibrating or colliding with each other. These collisions wouldn't necessarily destroy anything. Instead, they might have triggered something like our Big Bang. It's kind of like billiard balls smashing together, only instead of chalk dust, you get galaxies and stars, a truly cosmic game of pool, if you will. Now, some particularly mind-bending models suggest that these pre-existing structures, like the bulk in brain cosmology or the eternally inflating space, already contain certain conditions. These conditions could have acted as templates or seeds for what would become our universe's fundamental laws and constants, meaning the Big Bang wasn't a completely random event from absolute nothingness, but rather a transition from one state of existence to another within a larger framework. It's like saying your favorite cake didn't just spontaneously appear, it was baked according to a recipe, a cosmic recipe in this case. Let's visualize this for a moment. Imagine countless bubbles, each representing a universe with potentially different laws of physics, popping into existence within an ever-expanding space. Some bubbles might be incredibly tiny and short-lived, others vast and stable, and still others might have completely unrecognizable physical laws. Maybe gravity works in reverse, or the speed of light is much slower. It's a dizzying thought, isn't it? And to top it all off, some models even suggest that these universes could be connected through wormholes, cosmic shortcuts that would allow, in theory, for travel between them. Although, I suspect interdimensional road trips would require significantly more than just a tank of gas and a good map. Probably a whole lot of theoretical physics too. Okay, so we've spent some time dismantling the idea of a universe born from absolute nothingness in a single, explosive moment, the Big Bang. And you're probably thinking, alright, if not that, then how did we get here? Well, buckle up, because what if I told you that our universe isn't exactly new? What if it's just one iteration in an endless series of universes, like a cosmic recycling program where everything eventually gets broken down and rebuilt? These are cyclic models, and they offer some seriously mind-bending alternatives to the standard Big Bang theory, suggesting that expansion and contraction aren't isolated events but rather phases in an eternal cycle. Let's start with ekpyrotic cosmology, a name derived from the Greek word ekpyrosis, which means conflagration or cosmic fire. The core idea here is that our universe isn't expanding from nothing, but rather colliding and rebounding from another universe, existing in a higher dimensional space. Think of it like two sheets of rubber being pushed together then snapping apart. This collision generates the energy we interpret as the Big Bang, cleverly avoiding that problematic singularity. The infinitely small, dense point where our current understanding of physics just gives up. It's important to note that these aren't our universes in the sense of having planets and people. They are more akin to fundamental fields or structures existing outside of spacetime as we understand it. Now, imagine taking that concept even further, a universe so old that it has essentially forgotten its own past. That's where conformal cyclic cosmology, or CCC for short, comes in, championed by the brilliant and delightfully eccentric Roger Penrose. The central premise is that as our current universe expands and cools, eventually all black holes will evaporate through Hawking radiation. This process effectively erases information about size but preserves something called conformal structure, essentially the relationships between distances, which allows a future, vastly larger universe to recognize the previous one in some bizarre mathematical sense. It's like a cosmic game of telephone where the message gets garbled but still contains an echo of what came before. The really wild part about CCC is that Penrose believes we can actually see evidence of these previous cycles in patterns within the cosmic microwave background, CMB, the afterglow of the Big Bang. He posits that these are Hawking points, circular patterns corresponding to the locations of supermassive black holes that evaporated at the end of the previous aeon, leaving their imprint on the CMB. Now, this is highly controversial and heavily debated within the scientific community because finding definitive proof of something like that is incredibly challenging. But if Penrose is right, it would revolutionize our understanding of reality. Think about it. Not just a universe with a beginning, middle, and end, but an endless, ever-repeating dance. Visually representing these models can be tricky because we're talking about things happening in dimensions beyond our everyday experience. However, comparing them to the standard Big Bang is helpful. The Big Bang depicts a single point expanding outwards, a one-way trip from zero to everything. Cyclic models, on the other hand, show something more like a wave, oscillating between expansion and contraction, or perhaps two brains colliding in higher dimensions. It's less about a singular event and more about an ongoing process. You might imagine it as an infinite loop playing out across cosmic timescales, with each cycle slightly different, but still recognizably part of the larger pattern. Ultimately, these models are attempts to reconcile our observations with theories that avoid some of the most perplexing aspects of the standard model.